Alright, so we're going to look at one last type of problem. This is one that combines stoich with all this. So first one here says write the balanced equation for the decomposition of liquid water into its elements. So we're going to start with water, H2O, and it's going to decompose into H2 and O2. The 2's there because they're Brinkelhoff. And let's balance this. So we're going to need two waters to get us with one hydrogen molecule and two oxygen molecules. Alright, so now we're balanced. It says how many liters of hydrogen gas measured at 0.984 atmospheres and 32 degrees Celsius will result from the decomposition of 10 milliliters of liquid water. Now what we're going to need here is to realize that liquid water's density is 1 gram per milliliter. So we can immediately just change this milliliters to grams. If it was any other substance, I obviously would have to give you the density, but water's one of those things that it's a good idea to know the density of. So we're going to start with the stoich part first. We're going to figure out how many grams of hydrogen we would use, and then from that we can determine how many moles using the stoich, and that'll give us our N. We've got our pressure here, we've got our temperature here, we've got our R. The only thing we're missing is volume. Alright, so let's take a look. We're going to start off 10.0 grams of H2O. And if we look at the molar mass of water, I'm just going to go to the nearest ones place. I'm not going to go anything beyond that in terms of our sig figs for molar masses here. So 1 mole of H2O has a mass of 18.0 grams, and that's right from the periodic table. And now we're going to use our balanced chemical equation. We're going to change moles of water into moles of oxygen. It turns out that we have a 2-to-2 ratio. So if you want to keep it 1-to-1, 2-to-2, I'm just going to use 2 because those are coefficients. So for every 2 moles of water, we're going to have 2 moles of oxygen. And now we're going to change, well actually we're good. We can just leave it at moles of oxygen. If I do this, I should find that I get 0.556 moles of O2. Alright, so we've got our pressure here. We've got our temperature. Let's add 273 to it. So let's write down here our pressure is 0.940 atmospheres. Our temperature, after we do the adding of absolute zero to it, is going to be 305 Kelvin. We have our N. That's going to be 0.556. We're looking for volume, and the other piece of the puzzle that we're missing is R, but that's a constant, so 0.0821 liters atmospheres per mole Kelvin. Alright, so let's rearrange the PV equals nRT equation to get N all by itself, and we're going to get N is equal to PV over RT, and let's plug in our numbers. 0.940 atmospheres times I'm sorry, we're not looking for N. We're looking for V. Skip that. Everything up to this point is correct, so let's get V all by itself. So V is equal to nRT over P. Alright, so our N, 0.556 moles times 0.0821 liters atmospheres per mole Kelvin times our temperature, 305 Kelvin, all divided by our pressure, 0.940 atmospheres. When we do this, we're going to end up with I got 14.8 liters, just like the problem told us, 14.8 liters. So that's how we would do this. We got to figure out when we do the stoich. Sometimes it's first, sometimes it's second, but we can easily use stoich to get